have Lorenzo who will discuss about dimensional phase transition in interacting random.
Okay, thanks for the nice invitation, first of all. So it's a pleasure to be here. So this talk, yes, I'm going to consider a system of closed interacting random walk trajectories, namely a random walk loop soup, similar to those that have been considered in some previous talks. But the essential feature of the model that I'm going to consider is that we have an interaction between the loops. So they don't want to touch themselves and the other loops. And this makes the model this feature makes the model very challenging from a probabilistic point of view. And there is a motivation from statistical physics to consider this, or several motivations from statistical physics to consider this model. So I will first start from the definition and then discuss some motivations. Okay, everything I'm going to say takes place in the torus, on a finite set, torus of side length L. In dimension D. And we will consider the limit of increasingly large sets. So first I'm going to define, I'm going to tell you what is a loop. So let us define the set sigma and x, which corresponds to the set of closed random walk trajectories, which have length n and which start at x. So it's the set of trajectories. Namely, gamma I is going to be an element of lambda, such that the distance between two consecutive sides, or two consecutive elements of the sequence is 1, for each I 0 is 1. And the starting point corresponds to the last point, which is x. And we are going to now consider the set sigma, which corresponds to the union over all possible lengths and all possible starting points. So an element of this set is then just a closed random walk trajectory, namely a rooted oriented loop. So a closed random walk trajectory with an arbitrary starting point and an arbitrary length. And I'm going to denote by, I'm going to define the length of the loop gamma, length of gamma. Okay, so this is about the single loop, but in the configuration space of my model, I'm going to have an arbitrary collection of rooted oriented loops. So the configuration space of the random walk loop soup is denoted by omega, and I have union over 0 to infinity of the set sigma to the power of m. So which means that an element of this set is an ordered collection of loops. Namely, okay, what is an element of this set? I have some closed rooted random walk trajectories, and their number is arbitrary. And I'm going to define on this configuration space omega a probability measure, which is the following. So let me denote by absolute value of omega, the number of loops in the configuration omega, which is arbitrary number. And the random walk loop soup is defined as follows. For each arbitrary, for each configuration, we have a weight which depends on two parameters, lambda and alpha, and which is 1 divided by a normalization constant, and also depends on the size of the set. We are in a finite set. And then we have product over all loops in my system. And then I have a factor which depends on the loop, which is lambda to the length of the loop divided by the length of the loop. So if I had only this in the definition, I wouldn't have an interaction between the loops. And then I have, okay, I also forgot a term, which is 1 divided by the number of loops factorial. And the interaction comes here. And I will tell you later what is the interaction. So this defines the model. Okay, let us discuss the terms which appear in the definition. So we have our arbitrary collection of loops, but they can also have some self-intersection. Okay, I have first loop, second loop, third loop, fourth loop. So omega is an ordered sequence. So it counts what is the first loop, second loop, and so on. And if I give you a loop configuration with all distinct loops, how many possibilities I have to assign these labels? So how many possibilities I have to decide what is the first, the second, the third, and so on. I have number of loops factorial possibilities. And this term is a normalization for the number of possibilities that I have to assign these labels, to decide what is the first loop, second loop, and so on. Okay, then in the weight, I have a product over all loops. Then I have lambda to the length of the loop divided by the length of the loop. So if the loop okay, so I can think of this factor as a normalization for the number of possibilities that I have to decide what is the root. Okay, so this is a rooted, this is a loop with a starting point here. If I shift the starting point, I decide it's not this one anymore, it's this one, I obtain a distinct loop. And I have many possibilities to decide what is the root. And you can view this term as a normalization for the number of possibilities that I have. Okay, and I have to tell you what is the interaction, but this I'm going to tell you in a moment. First, do you have some questions about this definition? Okay, so the case alpha equal to 0. Okay, in this case, I don't need to tell you.
Do we care about, so the loops are still oriented?
They are, yes, they're oriented, yes. Yes, these are, so the single space of the single loop is defined here, and we care about orientation. Okay, when alpha is 0, okay, I don't need to tell you what is U. In this case, the model corresponds to the so-called random walk loop soup. And it can be defined in a completely different way. It can be defined as a Poisson point process on the space of unrooted loops with a certain intensity, which is, intensity will be intensity 1 in this case, when lambda is equal to 1 divided by 2d, which is the case in which the single loop receives a weight, which is the random walk weight, so 1 divided by 2 to the power to the length. And okay, and then this model has been studied. It has been introduced by Lowline and Ferrares. It has been proved convergence to Brownian walk loop soup. And also the percolation problem, so understanding the size of clusters of loops has been also addressed by several authors. But this talk is not going to be about the alpha equal to 0 case, because we're going to have an interaction between the loops. And this changes completely the phenomenology of the model. And okay, now it's the time to tell you what's the interaction. Okay, let me call this not you, but I, that they have the same. So what's the interaction? So I is going to be the intersection local time. This means that essentially we pay a price every time we have visits of the same loop over of different loops at the same vertex. So we have self-interaction within single trajectories and interactions between one trajectory and the other trajectory. So so this intersection local time is then as the contribution of mutual interactions and of self-interactions. Omega, as I told you, is sequence. Consider an arbitrary realization omega. So okay, here I'm going to have the mutual interaction term. So I have f gamma j. So consider all possible pair of loops. And then I consider all loops. And there's some other term, which is the self-interaction. Okay. So f gamma j, what I need to do is to for I different from j, what you need to do to define is just sum over all possible steps of the loop I and all possible steps of the loop j, and then count how many times the mth step of the loop I is on the same vertex of the of the nth step of the loop j. Okay, so this is the mutual interaction. And this is the self-interaction. Namely, U gamma, so the self-interaction, and just count, consider all pair of steps of the same loop. And I count how many times have that the m step of this loop is on the same vertex of the nth step of the same loop. Okay. And for simple random walk, the intersection local time is a well-studied object. So the questions in which we are interested are the following. So now we have an interaction. We have a parameter. We have two parameters in our measure. We have lambda. So if lambda is larger, we are going to favor the length of the loops. So imagine you increase lambda. Okay, so you're going to make more likely to have longer loops. But on the other hand, as you start having longer loops, these loops start touching each other, and you start paying a price because of the interaction term. you have e to the minus alpha. So you have e to the minus alpha. It means you have a repulsion every time you have loops which touch themselves or which touch the other loops. And the larger is I, and the higher is the price you're going to pay. And we want to understand what can we say about the size of the loops in the infinite volume limit. So we take our box larger and larger, about the geometry, and about the phase diagram of this model. Okay, let's now, okay, this is the definition. Do you have questions?
Lorenzo?
Yes?
This is different from analyzing the loop by the exponential of minus alpha times the sum of local times squared?
No, it's precisely the same. So you can, it's e to the, so this number, if you write this number, it's e to the minus alpha, then you sum over all vertices, and then you have local time, okay, it's not local time squared, it's local time times local time minus 1 divided by 2, because it's squared. So it's local time choose 2. So it's like the square, it counts the square of the...
So if I think in terms of the problem with Gaussian field, it's a bit like studying the 5-4 model.
Yes. Exactly. So you can write this measure to this term in this way. So, okay. So motivation. Okay. So in quantum mechanics, there exists a model called Bose-Gas, which can be reformulated as a model of interacting random walk loops through the Feynman-Katz formula. And this model describes a gas of bosons, and it is conjecture, well, actually it's known also experimentally that when the temperature is extremely low, there exists a phase transition in this model, which is called Bose-Einstein condensation, which can be related to the occurrence of macroscopic loops. But this is all in dimension at least 2. Sorry, at least 3. And, okay, the rigorous proof of this conjecture for the Bose-Gas is an open problem. But essentially, the model that we are considering is a toy model for the Bose-Gas. And here we can observe, we can prove rigorously the occurrence of this phenomenon. Second motivation is, and I will come back to this connection maybe later. Second motivation is, I think it's interesting also to have an understanding of what happens in this model, to consider this case, the case in which I have a single loop which is drawn at random with that weights. So, which means, okay, the motivation is due to relation to self-avoiding work. So now I define essentially a related measure, but just with a single loop. So let me consider now the space sigma, which I defined before, set of rooted closed random walk trajectories with arbitrary length and arbitrary starting point. And for each element in sigma, which is a rooted closed-oriented random walk trajectory, I define this measure, which I now called p tilde, depending again on both parameters. what is the weight? It's the same, the weight of the single loop there. So I have 1 divided by a normalization constant, and then I have lambda to the length of the loop divided by the length, and I have an interaction term where, okay, I have a single loop, so I will just have the self-interaction term. Okay, this model, or a variation of this model has been studied, and the problem of, and this question has been addressed and partially answered for this model. So in which I have a single random walk loop. And in particular in the case where alpha is infinity. So if I take alpha infinity, this means that I give an infinite penalization to trajectories which have some self-touching. In this case, I obtain the strictly self-avoiding walk. Okay, so, and it is known, it is an adaptation of a result of Duménil, Copen, Kozma, and Yadin. So it's a different setting, but I think the result can be adapted. That, okay, if we consider the strictly self-avoiding walk, and we take lambda large enough, greater than a certain 1 divided by the connective constant, so mu is d between d and 2d minus 1, which is the connective constant of zd. Okay, we ask, okay, let's draw at random for this choice of parameters a walk according to this measure. What I'm going to see? I'm going to see a walk which is weakly space filling. Okay, the starting point does not matter since I'm the torus, so I can say it starts from the origin. So essentially, I'm going to see a walk which explores the whole torus, and okay, it does not visit exactly every vertex. It leaves some empty regions, but the size of the regions which are empty is of the order of the logarithm of L. And why we have this behavior? Because it's interesting to have an intuition of what happened in this model. So that why we have this behavior, why if lambda is large enough, we have this, okay, not simple random walk behavior. Okay, the reason is that if we ask what's the number of self-avoiding walks of length n, starting from x, in the torus, but let's say that n is a very large number, but much smaller than the boundary. So now you don't feel the boundary effect. Okay, the numbers of self-avoiding walk starting from any vertex it grows exponentially as this constant to the power of n, asymptotically. So if now I tell you what's the probability that the length of our walk is going to be n, conditional that you start from any point, it does not matter. Okay, so this probability, okay, just have to consider the weights coming from this measure. Alpha is infinity, so this means we are considering only the case where you have self-avoiding walk trajectories. So this weight is going to be lambda mu to the n divided by n. So if so this divided by n does not play a big role, but if lambda mu is strictly greater than 1, you see that you are in the regime in which longer trajectory gets higher weight than closer trajectory, than shortened trajectory. So you try to maximize the length up to filling somehow the boundary. And okay, the proof requires showing that essentially you pay a cost not to visit one region because because it's in the regime in which the entropy wins. So you want to fill regions, and you have many possibilities to fill empty regions. So this result is essentially this phenomenon holds in any dimension, and I would expect that even if you don't consider the strictly self-avoiding wall case, but you just have some alpha positive, then the same holds as long as lambda is greater than a certain critical value, lambda critical. Okay, but now we are going to ask whether we observe the same phenomenon in the random walk loop soup. And, but from this point of view, the problem is harder, because if you try to understand the law of a single loop, then as long as your loop is in a region which is visited by the other loops, you pay a price. And you have repulsion. So it's a much harder problem to face from this point of view if you have the system of interacting random walk loops. Also because it's not hard to show that if in the random walk loop soup that if you take one region, if lambda is large, this region will be visited by some loops, but it's much harder to show that, to understand whether these loops are macroscopic. So it's not hard to show that the space is filled, but you want to show that it's filled with long loops. And indeed, we are going to see a different phenomenon for the random walk loop soup. So only if the dimension is at least 3, we observe macroscopic loops. So the dimension plays a role. Okay, last motivation.
What do you mean exactly by weakly space field? Do you have an estimate on the background?
Yes, so essentially this means that if you consider the set of sides, so you can consider the set of sides which have a distance at most a constant from the trajectory, then take the complementary of this set. The complementary of this set is such that the largest connected component is a size at most log of L times some constant. So,
sorry. Space filling means that in every proportion there's a point with trajectory.
Now, space filling means that your trajectory is going to fill almost the volume, but it leaves some regions which are empty, which are not visited, but the size of these regions which are not visited is small.
Okay, but how can n be much less than L when it should be compared to L to the D?
Okay, this argument, okay, this is not a proof, it's just showing you that there is a phase transition in this model when lambda times mu is greater than 1. So you, in the sense, you see that if lambda times mu is greater than 1, then longer trajectories get higher weight than shortened trajectories. This is true as long as, okay, of course, if n is too large if compared to the boundary, this is not true anymore. But as, just an argument that tells you actually in this regime, your walk tries to be long, wants to be long. Okay, so, okay, final motivation is for the random walk loop soup is now consider the random walk loop soup when alpha is infinity. So when alpha is infinity, okay, which model, what do we obtain? So the measure is a well-defined measure, and that assigns a weight 0 to trajectories which have some overlap. In this case, you have a loop of strictly self-avoiding, so a system of strictly self-avoiding loops, which are also disjoint. So lambda is positive, and take alpha to infinity. Okay, this model can be related to a model in statistical physics, which is the double-dimer model. With some vacant set. So it is a model which is also well studied and which is well understood on planar graphs. And not because there are some methods to understand this model on planar graphs due to Castellane's work, essentially. From the 60s. And, but it's interesting to understand what happens beyond planar graphs. And we are going to see some answers also in this regime when alpha is infinity. Okay, I don't want to define the double-dimer model, but essentially, if you take alpha infinity first, and then you take lambda to infinity, you have a system where every vertex belongs to a loop. So these trajectories are fully packed, and this corresponds precisely to the so-called double-dimer model. Double-dimer model. Okay, let's see now some answers to the questions we asked. I can explain more this connection if you have questions later. So results, okay, first result about dimension 3 and higher. Okay, take an arbitrary, okay, alpha is positive. Okay, first let's take dimension at least 3. The theorem tells that there exists a critical value of lambda finite, such that if the weight lambda is greater than this critical value, then the following happens, namely for each L, which must be an even integer, and for each pair of sides, we have the following two facts. Okay, let's call gamma x omega to be among all loop. Okay, define among all loops touching x, choose one uniformly at random. And if x is not visited by any loop, this is the empty set. If I have 5 loops visiting x, it's one of them chosen at random. Okay, the first result tells that if I ask what's the expected size of this loop, this is going to be to grow as the volume. The second result, okay, is stronger and is saying that the probability that there exists a loop connecting x to y, namely the probability that x and y belong to the same loop, is also uniformly positive. So I have my torus, take any pair of vertices with uniformly positive probability, even if these vertices are very far from each other, I will have a loop which contains both vertices. Okay, and this is true, okay, if lambda is large enough. So the expected loop length, so if you take the typical loop crossing any vertex, this is its length is going to be proportional to the volume, and take any pair of vertices with uniformly positive probability, you will see a loop visiting both. So we have macroscopic loops in the sense that is stated by the theorem. Okay, we have then a new result in dimension 2.
So is this for all L in what, sorry?
Yes, for all L must be an even integer. So it's somehow it's
if it's odd, is it false?
no, it's also true, but I think for this model, but no, okay. So if n is odd, okay, I don't know actually, because if n is odd, if you take the alpha infinity limit, okay, you also expect the same phase transition, but you cannot. So the model is not well defined anymore when alpha is infinity. So essentially, it's something different may be happening. So if you have an odd number of sides in your torus and you take alpha infinity, this model. Okay, it's also, well, okay, let's say that the theorem, so the technique that we use holds when L is even. Okay, and in dimension 2, this is a joint work with Weivu and, okay, the result is, quantitatively, it's very weak, but it's also strong enough to tell you that something different is happening than in dimension 3 and higher. So consider 2 dimension. All alpha. This alpha, as I said, can be an arbitrary positive number, but you can also have alpha infinity, which is this corresponds to the double domain model with some vacant set, and the results is about absence of macroscopic loops in the same sense as dimension 3 and higher. Is then about all lambda, for all lambda, possibly also again okay, it states that the expected length of the loop touching an arbitrary vertex divided by the volume, L squared, is not uniformly positive as in the statement 1 of the first theorem, but it's going to 0. And the bound that we have is relatively weak, but tells you that you are not in the same situation as in dimension 3 and higher. And also what we expect actually, but we don't know in dimension 2, we expect a so-called Kosterlitz-Thouless phase transition, namely we expect the probability of a loop connecting 0 to x to behave as e to the minus the distance if lambda is smaller than a certain critical value, and 1 divided by the distance to some power b if lambda is greater than a certain critical value. So namely, we expect, so in dimension 3 and higher, we have a transition from exponential decay and no decay. In dimension 2, we expect a transition from exponential decay to polynomial decay, which means that this expectation, when lambda is large, we expect to grow polynomially with a power smaller than 2 in dimension 2 if lambda is large. And the expectation is not going to grow to infinity otherwise. Do you have questions? Okay. Also, the theorem holds for more general interactions. So we can define the random Markov soup in with interactions which do not necessarily need to be the intersection local time.
So the first theorem is about large lambda.
Yes, the first theorem is about large lambda, exactly. The second theorem is about all lambda.
Right. So do you have existence of a phase transition in the high dimensions?
Existence of yes. Yeah, okay, I didn't write it. When lambda is small, we always know that this happens. It's not hard to prove. When lambda is small, it's always decay in wide generality. You always have exponential decay. Yes?
Okay, so in the two decays, so you have the volume is small, you also know that the diameter is small, or?
I think I don't have information on the diameter. So, yeah, so quantitatively is a weak result, but okay, it's strong enough to say you're a different situation than dimension 2. So okay, there are some extensions in the sense that okay, it's also that you need to take a planar graph. For example, if you take a box where k is smaller than square root of log L, then the theorem is also going to hold. And this is relevant in the framework of the Dimer model, for example, that you don't get planarity. And also, okay, also for more general interactions. Okay, so.
Sorry, but there's no monotonicity.
No, it's not known. That,
So
I mean, no, we expect, but for this type of claims, you need some correlation inequalities usually, since you have no independence, and we don't have this correlation inequality.
Why do you expect crystalline star less?
Yes, this is based on the fact that we have a, actually maybe I would say in the proof that we have essentially we can represent this this model as a spin system, as a non-classical spin system with some complex measure, for which should behave as an XY model, and then because of this connection we can make this.
So therefore, you do not get this when alpha is 0?
Sorry?
Do you therefore not get this when alpha is 0?
When alpha is 0,
Then you have no like pi 4 term.
yes, exactly. When alpha is 0, okay, in the non-interacting case, actually the model is even not well defined in the way as I define the way that when I take lambda strictly greater than 1 divided by 2d. If we consider the definition that I gave, because the partition function becomes infinite. So I'm giving to, but okay, you can define it as a Poisson random walk groups. Then okay, in this case, I don't know what's, okay, I will, so that will mean that, okay, essentially, if in the non-interacting case, if lambda is smaller than 1 divided by 2d, I'm always in this situation. If lambda is equal to 1 divided by 2d, I have simple random walk behavior. And if lambda is greater than 1 divided by 2d, the model is not well defined in the way as I define it. But if alpha is positive, it's always well defined. There is not this problem of infinite trajectories. Okay, so I still have time. Okay, so actually, so this model is not too much related to random walk as alpha is positive. So for example, if you consider the single loop, when alpha is 0, you have simple random walk. So alpha is 0 and lambda is 1 divided by 2d. But as long as alpha is positive, you have a self-avoiding walk, a weakly self-avoiding walk. But weakly self-avoiding walk behaves differently in terms of universality class from simple random walk. If you are okay, but the properties of simple random walk in this model are relevant if we ask a different question, namely, how fast does the critical curve approaches the 0 case? Okay, so I define two models. So I can talk 5 minutes about this. I have the single loop measure, single walk. So it's the second measure I define. We have a single closed random walk trajectory. This is P tilde. And P is instead if the random walk loop sup, which depends on this parameter lambda and alpha. Okay, and so we can plot two phase diagrams. This is for P tilde, namely the single walk, and this is for P. Here you have alpha, here you have lambda. Okay, and when alpha is 0, the critical values are the same, 1 divided by 2d. And then we have a critical curve. Okay, if the interaction are stronger, then you need a bigger value of lambda to observe macroscopic loop. So this is increasing. And so this is the single random walk, so it's increasing to a value 1 divided by the connective constant, which is the critical value of the self-avoiding walk. And here it's increasing to okay, another value, which is the critical value of the so-called monomer double dimer model. Okay, and if we are here, we observe short, the walk is short. And here we should be weakly space filling. And here the loops are short. Namely, we have exponential decay of the loop length. And here we have macroscopic loops. So I'm considering here dimension at least 3. Okay, and then we ask how fast does the critical curve, so here we have a critical curve lambda c alpha, and here lambda tilde c alpha. How fast does it approach 0? We have a conjecture, which is for the random walk loop sup, is that lambda c alpha, if you consider the limit as alpha going to 0, this is 1 divided by 2d plus a linear term where u is a positive constant. And then we want to understand what's the second order term. You have c alpha squared times a logarithmic correction if d is at least 3, and no logarithmic correction, sorry, if d is at least, if d is 3, and no logarithmic correction if d is at least 4. And this question about how does the critical curve approaches the alpha 0 case is also a question from physicists involving the Bose gas. Essentially, in experiments, you need to, so this phenomenon has been observed only, first time in the 70s with an experiment for which the Nobel Prize for Physics was given, and the experiments require taking an extremely small interaction. And this is maybe one motivation to consider this regime of alpha going to 0. And there are some conjectures about how does the model behave when alpha going close to 0, which you can answer by understanding what's the second order term in this expansion. And we can ask the same question for the single random walk. And this is somehow a question that I'm addressing with Matteo Quattropani. Okay, we can show that for the single loop, but this, I mean, it's not, this is an intermediate step to the conjecture, we hope. This is 1 minus alpha u, and it's greater than 1 divided by 2d minus alpha u minus alpha squared times log 1 divided by alpha 1 plus epsilon. and times 1. So essentially, answering this question requires a good understanding of the model when alpha is 0, which means simple random walk or closed simple random walk for the single loop. And one can answer this question by understanding how does understanding the moments of the self-intersection local time of simple random walk. For example, this different behavior depends on the fact that the variance of the self-intersection local time of a simple random walk of length n grows as n log n in dimension 3 and as n in dimension 4 and higher. This reflects on a different behavior here. So if we want to understand, okay, prove this conjecture instead, okay, this is a conjecture. For the random walk loop soup, we will need to have a good understanding of the model when alpha is equal to 0. So this is the case where we have no interruption. Yes?
So just to clarify, because there's no monotonicity in lambda, you have actually a critical value, a unique critical value, or?
No, we don't have a unique critical value.
So what does that actually mean then, the statement?
For inequality, you don't need to define it, right?
What?
I guess this
For inequality, you don't need to define the critical value.
Essentially, if you had monotonicity, this will be well defined, and then it will satisfy this inequality. But the proof, okay, the upper bound, so this requires showing that if you take lambda smaller than this, then you have exponential decay, and that you don't have exact. Use, yes, here is just a constant, but if you want to know the precise definition, this constant is going to be the expected self-intersection of the simple random walk of length n divided by n. In the limit, this will converge to a constant, and this is going to be this constant.
Do you press that value?
Yes, sorry. Yeah, thanks. But okay, essentially this follows from known results from about the self-intersection local time. This is the conjecture, and this was a message to say actually simple random walks play a role if you want to understand how fast does the critical value approaches 0. So okay, now in the remaining time, I will tell you something about the proof. So proof of the main theorems.
I'm sorry, just to make sure, the u on the right-hand side is the same as the one on the left-hand side?
No, that's not the same. That actually I expect here to be 2u. But I'm not completely sure. It's not the same. Okay, and okay, so when alpha is positive, so we cannot expect for the theorem 1 and 2 to use simple random walk techniques. We use a completely different approach. Okay, so the goal is to understand the behavior of the two-point function. Namely, the probability that we have a loop connecting 0 to x. And, okay, essentially, the proof in particular of the second theorem, so I'm speaking more of the proof of the second theorem, consists in showing that this model is equivalent to a completely different model, which is a spin system. So we find a spin measure, which I denote with the physics notation. Spin measure, which allows us to make a parallel between this G and the spin-spin correlation in the spin measure. So this probability is going to correspond to some spin-spin correlation. Okay, if we had the easy model, the spins will take value 1 or minus 1. If we had XY model, this will take value in the unit circle. But here, the spin is a pair, and which corresponds, which you can write as e to the Sxi e to the minus Sx2. So you take value in C2, where Sx1, Sx2 are some angles. So we have some spin measure. Okay, I could define it, but there is no time, and it also takes time to define it, which makes possible to reformulate questions about the decay of the two-point function as questions involving the decay of a spin-spin correlation in spin systems, and this connection has been found in the second paper. And we can use then methods from spin systems to understand then the decay of this probability. If you understand the decay of this probability, then okay, you can prove the theorems that I stated. And there are two main techniques. One technique which is used to prove that dimension 3 and higher, that it's called the infrared bound method from Föhlich, Simon and Spencer from the 76, I think, which is used to prove that if you sum over all sides in the torus G0x divided by lambda L, and you take lambda large, well, lambda should play the role of the inverse temperature, then this is uniformly positive. Okay, and this sum can be related to the expected loop length divided by the volume. And then we have some site monotonicity in X, which also allows to derive more detailed results. And okay, it's related to the expected length, this sum. It's the sum over all vertices of the probability of 0 visiting X. And in dimension 2, there is another proof method, which is called Mermin-Wagner theorem, which instead used to show that the sum, this sum goes to 0 as L goes to infinity. But what is the difficulty in applying these results? The difficulty is that the spin system that we have is not a probability measure. Namely, it is some complex measure. So it's not a positive measure, it's a complex measure. And then you cannot apply the classical proofs in a direct way. So essentially for the second theorem, we derive a new Mermin-Wagner theorem for complex measure, using as a tool a correlation inequality which is called reflection positivity, which is an ingredient which has been introduced by Föhlich, Simon and Spencer in the 76. And so we derive a new Mermin-Wagner theorem using reflection positivity, and the validity of the theorem holds, and the proof does not require having a positive measure. So yes, so I have negative time, so I will conclude here.
Questions?
Please tell more about this
measure. Yes, so I mean, if I define the measure, I think it takes at least 5 minutes. So I will prefer to, maybe it's not, okay, it is a spin system so that you can write as, okay, if I write the partition function I am integrating, okay, but that does not take, just say it short. So we have a product of Lebesgue measure, and where the local spin space, essentially each spin corresponds to a pair of angles. And then I have some complex function here. So this is GS is going to be a complex function, and they will need to tell you what is precisely this function. And then I have a classical Hamiltonian. So essentially it's an XY model in which the spins are pair e to the I sx1, e to the minus sx2. Each spin is a pair, can be identified with a pair of angles. And they have the classical definition into the minus an Hamiltonian and so on, where it appears the product of the spins. But the point is that I have a complex weight here. And okay, we'll need to tell you what's the complex weight. I can do it maybe later. I can write it. Yes, exactly. It's not a probability measure because here I have some weights which are not just positive weights. But yeah. But this number, which is going to, for example, this is the partition function, is a positive number. It corresponds to the partition function of the random Markov soup. But if I want to write as an integral with respect to some spin measure, then I have to take here complex factors. And if I want to write the probability that 0 is connected to x, okay, this is a positive number. It makes completely sense. As a probability measure, it's a probability of some event in the random Markov soup. But if I want to write as in terms of the spin measure, okay, because here I'm going to have the correlation and I'm going to integrate with respect to a complex measure where these complex factors appear. This means that if I want to use classical proofs, because these factors are complex, I cannot use, for the spin measure, Cauchy-Schwarz inequality in a useful way. So one needs a different approach. And this is the new proof of Melvin-Wagner theorem.
Is it really phi x1, phi y1, or is it, there's no bar?
No, so
As in you take e to the
so
I.
okay, there are
ideas.
So if you want to know the exact, so it's actually okay. You can write if I have my angles. This is the spin at. Okay, if I use the angle parametrization, this will be e to the I sx1 minus sy1. So yes, it is with a minus. So it's. And these are now, so this is angle parametrization. These Sx are angles between 0 and 2 pi. But, so depending on what I plug in here, I get a different object for the random Markov soup. Yeah, so I can look at other observables for the random Markov.
Presumably there's a reason why you decided to write either the I at x1 and minus I. Presumably there's some reason as to why it is you've written them with...
yes, exactly. That's true, yes. Well, it's just a parameterization. I can also write a plus, but yes, I would like to say as somehow the product in C between the spins.
Jean-François.
It would be interesting to
Consider a continuous version of the model with the Brownian loops interacting with their
Yes, it could be interesting. I think very interesting. Just I don't know how to approach this question. But okay, here essentially one using in a essential way this connection between spin system and model.
For Melvin-Wagner in general, do you have a version also where you have polynomial decay of correlation by deformation that
No,
you get that or not?
So the point is that here I said Melvin-Wagner, so the classical proofs uses these rotations, but we use older approach which is due to Mermin, which also provides, which relies only on providing some bounds on the Fourier transform of the two-point function, where we don't have this polynomial with the. So we don't have polynomial. So the only information that we can get is really that this sum is going to 0. So it's even weaker than the classical Wagner. Because it's a different, okay, so it's a, as I said, the classical strategy does not work. One needs to do things differently and the result is weaker.
So when there's no interaction, does your random walk soup correspond to the one which is related to the Gaussian free field?
Yeah, so it corresponds, yes, to the so-called random walk loop soup, yes.
At which intensity? Is it the intensity of the...
No, exactly. So if you want to, it's intense. So if you want, I define a measure which was, okay, this factor. No, so this factor, to make the connection, lambda must be 1 divided by 2d. So you have to give to each trajectory a simple random walk weight. If you want to have this correspondence to a random walk loop soup with a certain intensity, say intensity n, you need to add in the definition of the random walk loop soup a factor n to the number of loops. This will correspond.
So your n here is equal to 1?
Yes, and here it's equal to 1.
And is it?
Or it's maybe n divided by 2 to make the correspondence. So it depends if you consider oriented or non-oriented. So, okay.
Still, so when lambda is equal to 1 over 2d, you have a connection with the Gaussian free field?
Yes.
And okay, and now if lambda is not 1 over 2d, it's just a massive version of this, no?
Yes, if lambda is smaller than 1 divided by 2d, I would say yes. So I should have. So I have exponentially small loops and
so actually, if I were interested in the two-point function, like not for a loop but for a cluster, I could use the Gaussian free field, or actually the by 4.
In the non-interacting case, you mean?
No. So
okay.
now I also add interaction. So this means that I'm adding interaction to my Gaussian free field.
Yeah, maybe there is this connection also.
And so okay? So my question is like, is there a way of using the Gaussian free field to get direct estimates for this, but when you are not interested, when you want to realize connections with the cluster instead of
okay, so you mean this connection with Gaussian free field probably gives you information on the cluster, but studying the cluster is actually easy also from the, I don't need this connection. Since if I want to, for example, if I want to study the percolation problem for this model, I can do it without Gaussian free field. So here the question is how to relate, it's about the loop connectivity, it's not the cluster. So the cluster is easy. And so I don't know how to make this connection with the Gaussian free field in this case.
Can you remove the self-interaction of loops in your interaction? So just consider interaction between different loops.
Yes, so I mean I can remove it. No one tells me, you can do it, but I don't know how to get results in this case. So in the sense, okay, it plays a role that I can rewrite this interaction as a sum of local terms. And the local term will be local time choose 2. It will be local time at x squared somehow. So I need to have this, the total interaction must be written as a sum of vertex factors, of quantities which depend only on how many times the vertex is visited. And this is true if I do not distinguish in the measure the visits from the same loop or from other loops. If I distinguish, so if I only weight some of them, then the technique that we used does not work because I told you there is a tool which is correflection positivity and this, okay, I didn't tell you what it is, but it requires this local description.
You mean here Lx is the total?
Yes, Lx is the total number of times x is visited by some loop. So essentially this interaction can be written as a sum of Lx choose 2.
No more questions. I think Lorenzo